Hi everybody, this video today is going to talk about friction. So let's just take a minute to read through the definition here. Static and kinetic friction forces are contact forces that act parallel to the surfaces in contact. The direction of the kinetic force will always be opposite the direction of motion. The direction of the force vector for static friction is usually opposite the direction of the intended motion. But you must be careful to look at all information closely in order to determine the actual direction. For instance, a stationary box in the back of a pickup truck may have static friction force in the direction of the acceleration vector. So, kind of a summary of that is that the friction force is parallel to the surface and it is usually opposite of the direction of motion. When we in this class talk about static friction and kinetic friction, we use our capital F for friction and then the capital F for force and then the lowercase f for friction and then S for static. So this is static friction, this is kinetic friction. And we distinguish between them because we saw this the other day when we were pulling the wood block with the spring scale, that when you pull it with that spring scale, the static friction is actually higher than the kinetic friction. And so we will distinguish between whether it's static friction or kinetic friction. So static frictional force varies from 0 to some maximum value by this inequality. And we actually, maybe instead of using that one, let's write it this way. Because we use our capital F for the AP, we use the capital F and then lowercase s for static. I should put an F in there. And then the mu is this letter is the mu, and mu is the Greek letter for m, and it's just what we use for static friction. I don't know why we use the mu, it's just what we do. And then this is the normal force. So whatever the normal force is, we take the normal force times the coefficient of friction, and that gives us the total amount of friction involved. And so here we have another equation. This time we're talking about what about the maximum value? And there's a slight differentiation because remember that like when we were pulling this with our spring scale, you could pull, and your spring scale is like reading higher and higher and higher until finally it moves. So there's actually a little bit of a range in there with our static friction. And so that's what was happening here. That's why it's less than or equal to, is because you can pull a little bit or a little bit more, or a little bit more, a little bit more. And it's not until finally that kind of breaks through that it reaches its max. So the max value is this, and this is for static again, is mu times the normal force again. And again, we might rewrite this as this. So it's the same equation, it's just that this is the max value of it, whereas this is all of those little intermediaries between there. Okay, and then here we talk about what this mu is. In this equation, mu sub s is the coefficient of static friction, which is a constant dependent on the surfaces in contact. And n, which we call F sub n, is the magnitude of the normal force. So I can show you in class a table that has different values on it, but basically consider like ice on ice. Okay, that's going to have a very small coefficient of friction, whereas Velcro might have a very high coefficient of friction. And so the constant is that mu. That'll tell us how slippery or how frictiony a certain surface is. Kinetic friction occurs once the static force has been overcome. So back to this thing where we're pulling that wood block with our spring scale. Once it's overcome, then it kind of maybe glides a little bit, but it has that frictional force. That's the kinetic friction now. So the coefficient of kinetic friction is usually less than the maximum coefficient of static friction. And again, we saw that. We pull it, we pull. It finally kind of breaks through, and that's when we start getting the coefficient of kinetic friction. The equation for kinetic friction is very similar again. It's just we're changing this to F. I can write it over here. The kinetic friction, but we're still taking the mu times the normal force. So if you were just kind of like memorizing a general formula, which you don't have to because it is on our formula sheet, you would just say that the frictional force is mu times the normal force. But again, this is all on the equation sheet, so don't worry about memorizing. Okay, so in this equation, mu sub k is a coefficient of kinetic friction, which is a constant dependent on the surfaces in contact, and n, or F sub n, is the magnitude of the normal force. And so once again, that's going to vary whether you're talking about ice or sandpaper or Velcro or whatever. Okay, let's take a look at 48. Skip this note, don't worry about that. 38 is where we're going to pick up. When drawing free body diagrams, how are the friction vector and the normal force vector always oriented with respect to each other? And they're going to be perpendicular. So for instance, we know that if we have the force of gravity working straight down, well, the normal force is always perpendicular to the surface that it's sitting on. So this is our normal force. And so if we're, for instance, if we're dragging something, let's say to the right, then the frictional force is acting the other way. But what we're talking about here is that the friction force and the normal force are perpendicular to each other. And so if we look at the case of something on a ramp, then we have a normal force here, we have the gravitational force here, but again, let's say this item, whatever it is going downhill, so our velocity is going this way. Well, in that case, our frictional force is going to act this way. And so our normal force and our frictional force are perpendicular to each other. So the frictional force and the normal force are always perpendicular regardless of what the orientation is of the surface. Okay, if we turn the page, number 39, a rope is tied to a 12 kilogram crate that is resting on a rough horizontal surface. The rope is pulled with a tension of 20 newtons at an angle of 30 degrees with respect to the floor. Find the static frictional force and the normal force acting on the crate. If the static frictional force is the maximum, what is the coefficient of static friction between the crate and the floor? All right, let's go ahead and start thinking about this in terms of a free body diagram. Of course, we're going to have the force of gravity, and since it's on a surface, we will have a normal force. And then we have the rope that is pulled with a tension of 20 degrees at an angle of 30 degrees with respect to the floor. So I'm going to draw a 30-degree angle here and say this is my force of tension, and this is 30 degrees. And that tension is a 20-degree Newton tension. Find the static frictional force and the normal force acting on the crate. Okay, let's start off with that. So if we start off with the sum of the forces in the y direction. Oh wait, we need to say our friction, don't we? Let's put our friction in here. And I have to say, I was not very careful with my lengths of my vectors, but we'll try to make sure that they all work out. Okay, so the sum of the forces in the y direction. What do we have going in the y direction? Well, we have the normal force acting in the y direction. We have the force of gravity acting in the y direction. And we also have right here this force of tension in the y direction also. So those are all of our y forces. Now we need to do a little bit of calculation and say what are those forces. So the normal force in this case is what we're looking for. We're going to leave that as the normal force. We don't know what that is. Gravity, of course, is mass times gravity, and the force of tension in the y direction, in this case, it is opposite, so it's going to be sine. The tension was 20 newtons, so this is going to be 20 times the sine of 30, and we're going to add those up to be equal to 0. Tension is going in the positive y direction. Normal is going in the positive y direction. We need to make sure when we do this calculation that gravity comes out to be negative, which it will because we're going to use a negative 9.8. So the mass is 12 kilograms, and the gravity is negative 9.8 meters per second squared, and we still have our 20 sine 30 over here. I need to go to my calculator and do those calculations and see what they come out to be. Okay, when I do those calculations, 12 kilograms times negative 9.8 is negative 117.6 newtons, and 20 sine 30 is 10 newtons. So I add those two things together and I get a negative 107.6 newtons. So in other words, the normal force is 107.6 newtons. Okay, that is our normal force. Now we need to talk about what about the sum of the forces in the x direction. And so if we look at our free body diagram, the sum of the forces in the x direction, we have a frictional force, and so it is static, so we can put a little s there. So this is static friction, and then we need the force of tension in the x direction, and those will add up to be 0. The frictional force is what we're solving for. The x direction on the tension would be adjacent, so that's going to be cosine. So it's 20 times the cosine of 30. Okay, so we go to our calculator, and 20 cosine 30 is 17.32. The force of static friction is a negative 17.32 newtons. And I'm just going to check my sign real quick. I'm going to go back to my free body diagram. It's pointing to the left, so I'm okay with that being negative. That makes sense to me. The last question says, if the static frictional force is a maximum, what is the coefficient of static friction between the crate and the floor? So we're talking about static friction, and our formula for static friction is mu times the normal force. And so that's what that last question is asking. It's kind of wordy, but they're just asking you to use this formula to find the mu, the coefficient of static friction. So we know static friction force is a negative 17.32 newtons, and we're looking for mu. And the normal force, we found that to be 107.6 newtons. And so now we just need to divide both sides. We divide both sides by 107.6, and we get 0.161 for our coefficient of static friction.